March 21, 1945, 32,000 feet above Tokyo Bay. Staff Sergeant Carl Hendricks sits in the pressurized forward upper compartment of a B-29 superfortress named City of Los Angeles, his hands resting on control handles that connect to absolutely nothing. Through the plexiglass bubble above his head, he watches 3 Kawasaki Ki-61 Tony fighters rolling into attack positions from 9 o'clock high, their olive-drab wings catching the late morning sun as they begin their dive toward his bomber. Every instinct screams at Hendricks to grab his twin 50 caliber machine guns, swing them toward the approaching threat, and fire. But his guns won't move. They're locked in place, aimed at empty sky 40 degrees away from where the Japanese fighters are currently flying. Hendricks's hands aren't on gun controls. They're on a computer site that feeds targeting data to a gunner somewhere else in the aircraft. Someone he can't see. Someone he's never met, sitting in a completely different compartment controlling guns through electrical impulses and hydraulic servos. The lead Tony opens fire at 800 yards, its twin 20mm cannons winking orange. Hendricks watches tracers arc toward his position and does the one thing that violates 23 years of human survival instinct. He does nothing. He trusts the mathematics. Somewhere behind him, in the aft upper turret he cannot see, Sergeant James Wu tracks the fighters through his own sight. Wu's turret swivels smoothly, powered by General Electric's remote fire control system, calculating deflection, altitude, temperature, aircraft speed, and 12 other variables in real time through analog computation. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Wu squeezes his trigger. 4 50 caliber guns that aren't even in his compartment open fire simultaneously. From 2 different turrets, their bullets converging on a point in space the lead Tony hasn't reached yet. The Japanese fighter flies directly into this invisible wall of lead. 23 rounds strike the aircraft in less than 2 seconds. The Tony's right wing separates from the fuselage at the root. The fighter tumbles away, spinning wildly as its pilot fights desperately to bail out. The remaining 2 Tonys break off their attack, rolling away before reaching firing range. They've learned what hundreds of Japanese pilots learned during the first 3 months of 1945. Attacking a B-29 wasn't like attacking earlier American bombers. The superfortress didn't just have more guns or better armor. It had fundamentally changed the nature of aerial combat itself by removing the human element from the actual act of firing, by trusting mathematics and machinery over human reaction time, by transforming defensive gunnery from individual marksmanship into centralized, computer-calculated probability. What Staff Sergeant Hendricks experienced that morning over Tokyo was the culmination of the most revolutionary transformation in aerial gunnery since the invention of the aircraft machine gun itself. Within 8 months, this system would help American bombers achieve defensive gunnery results that defied every prediction made by pre-war theorists. B-29 seconds, using central fire control, would destroy Japanese fighters at rates 3 times higher than B-17 seconds and B-24 seconds ever achieved over Europe, despite facing equally determined opposition from pilots flying lighter, more maneuverable aircraft. The revolution that enabled this transformation had begun not in combat, but in the sterile offices and drafty hangars of Boeing's Seattle plant in late 1939, where engineers wrestling with an entirely different problem inadvertently created a weapons system that would rewrite the rules of aerial warfare. The central fire control system that would give the B-29 its legendary defensive capability wasn't designed to solve gunnery problems. It was designed to solve a heating problem. When Boeing began serious design work on what would become the B-29 inches October 1939 under Army Air Corps project designation XB-29, the specifications called for an aircraft that could fly higher, faster, and farther than any bomber ever built. The preliminary design included a pressurized cabin, something no bomber had ever successfully incorporated. This wasn't luxury, it was necessity. To reach the required 40,000-foot ceiling and maintain cruise speeds above 300 miles per hour, the crew couldn't sit in unpressurized compartments wearing oxygen masks like B-17 and B-24 crews did. but pressurization created an impossible problem for defensive armament. Traditional bomber gunnery required men sitting at open or semi-open gun positions, their weapons physically attached to manually operated mounts. You couldn't have open gun positions in a pressurized aircraft. The moment you created an opening large enough for a gun to traverse, you lost pressurization. The engineering solution came from Boeing's Roscoe Cocking, a 38-year-old mechanical engineer who had worked on the company's flying boat projects. In January 1940, Cocking proposed a radical idea. Instead of placing gunners at their guns, place the guns in remote turrets and have gunners control them from pressurized compartments through electrical and hydraulic systems. The concept wasn't entirely new. Various remote gun systems had been proposed and tested throughout the 1930s. The British had experimented with remote turrets on the Boulton-Paul Defiant fighter. The Germans had tested remote systems on several prototypes, but no one had successfully integrated remote fire control into a heavy bomber, and no one had attempted to link multiple turrets into a centralized system where one gunner could control weapons located in entirely different sections of the aircraft. The technical challenges were staggering. A gunner sitting in the forward compartment needed to control guns mounted 30 feet away in the upper aft turret. When he moved his control stick right, the distant turret had to move right with zero perceptible lag. When he elevated his sight, the guns had to elevate instantly and precisely. Any delay, any slop in the system, any disconnect between what the gunner saw and where the guns pointed would make accurate fire impossible. Boeing partnered with General Electric, which had been developing remote control systems for industrial applications, and Sperry Gyroscope Company, which had pioneered gyro-stabilized fire control. The contract, signed in March 1940, called for a system that could control 4 remote turrets, 2 dorsal, 2 ventral, plus a manned tail position, all coordinated through a central fire control computer that could calculate deflection, altitude compensation, and parallax correction in real time. The prototype central fire control system was first tested on the ground at Boeing's Renton facility in August 1941, 4 months before Pearl Harbor. The initial results were disappointing. The hydraulic servos controlling the turrets responded too slowly. The electrical connections between sighting stations and guns suffered from signal degradation. The analog computer calculating deflection couldn't keep up with rapid target movement. Worst of all, when multiple gunners tried to control the same turret simultaneously, the system became confused, with turrets jerking back and forth between conflicting commands. Major James Eaker, observing the tests for the Army Air Corps, wrote in his report that the system showed promise but required extensive development before it could be considered combat-ready. He estimated 18 months of additional testing would be necessary. He had 12 weeks. The Japanese attack on Pearl Harbor on December 7, 1941, transformed the B-29 program from an experimental project into America's highest aviation priority. In February 1942, the Army Air Forces issued a directive. The first B-29 seconds would enter combat service no later than January 1944. Everything else was secondary. General Electric assigned its best engineers to the fire control problem. Sperry dedicated an entire division to the computing site. Boeing built a specialized test aircraft, a modified B-17 fitted with prototype remote turrets, and flew it continuously from March through August 1942, accumulating data on system performance under actual flight conditions. The breakthrough came from an unexpected source. Lieutenant David Perkins, a 26-year-old MIT graduate in electrical engineering serving with the Army Air Forces Material Command at Wright Field, Ohio, had been analyzing the system architecture. In July 1942, he identified the core problem. The system was trying to do too many things simultaneously. Each gunner could theoretically control multiple turrets. Each turret could be controlled by multiple gunners. The computer tried to process all possible combinations, creating processing delays and conflicts. Perkins proposed a radical simplification. Divide the aircraft into sectors. Assign each gunner primary responsibility for specific turrets based on attack angle. Let the computer automatically switch control to the appropriate gunner based on target bearing. If a fighter attacked from 10 o'clock, the left gunner automatically gained control of all turrets that could engage that sector. If the fighter rolled around to 4 o'clock, control automatically transferred to the right gunner. No more conflicts, no more confusion, just smooth, instant response. The first B-29, incorporating Perkins's sector control logic, took off from Boeing Field in Seattle on September 21, 1942. The Army Air Forces accepted delivery of the first production B-29 on July 8, 1943, at Boeing's Wichita facility. By then, the fire control system had evolved into the most sophisticated weapons system ever installed on an aircraft. The B-29's General Electric Central Fire Control System consisted of 5 sighting stations. The bombardier in the nose could control the forward dorsal turret and the forward ventral turret. The flight engineer, sitting behind and above the pilots, operated a sighting station controlling the forward dorsal turret. The left gunner, in a small pressurized compartment amidships, controlled the port side guns, the aft dorsal, and the aft ventral turrets. The right gunner controlled starboard and aft turrets. The tail gunner, sitting alone in the extreme rear of the aircraft, manned his position directly, the only gunner who could actually see his guns. Each sighting station featured a computing sight manufactured by Sperry. The sight incorporated a reticle with ranging bars. The gunner tracked the target, estimated range using the bars, and input wingspan from a table listing common Japanese aircraft. The computer, a mechanical analog device using gears and cams, continuously calculated the proper deflection based on target speed, bomber speed, altitude, and a dozen other factors. When the gunner squeezed his trigger, electrical impulses traveled through shielded cables to remote turrets. Hydraulic servos, powered by the B-29's hydraulic system, moved the turrets to match the gunner's sight picture. The guns themselves, 12 50 caliber Browning M2 machine guns distributed among 5 turrets, fired in perfect synchronization, their bullets converging on the calculated impact point. The system could track targets moving at up to 500 miles per hour, calculate deflection for engagement ranges from 200 to 1,000 yards, and compensate for the B-29's own motion through 3-dimensional space. Technical Sergeant Robert Morrison, who trained on the system at Lowry Field, Colorado, in August 1943, later described his first encounter with central fire control. They sat us down in front of these sighting stations, and I thought they were joking. There were no guns, no ammunition, just this periscope-looking thing with a trigger. The instructor said when we pulled that trigger, guns somewhere else on the airplane would fire. It seemed like magic or maybe a bad joke. The training program for B-29 gunners, centralized at Lowry Field and later at other facilities, reflected the system's radical departure from traditional gunnery, where B-17 and B-24 gunners spent weeks learning to physically handle their guns, clear jams, adjust for wind and G-forces. B-29 gunners learned to trust instruments, read dials, input data, and above all, believe that when they aimed their sights at empty air, guns they couldn't see were pointing at the same empty air. The psychological adjustment proved more difficult than the technical training. Master Sergeant William Erickson, an instructor at Lowry Field, noted in a training report from November 1943, "The biggest challenge isn't teaching the mechanics of the system. It's convincing students that it actually works. They want to see their guns. They want to feel the recoil. They want physical confirmation. We're asking them to trust electronics and hydraulics with their lives." The B-29 seconds began arriving in India in April 1944, assigned to the 20th Bomber Command under Brigadier General Kenneth Wolfe. The initial combat deployment, Operation Matterhorn, involved flying missions against Japanese targets in Southeast Asia and eventually Japan itself, using forward bases in China. The logistics were nightmarish. B-29 seconds had to fly fuel and bombs over the Himalayas to Chinese bases before launching strikes. But the fire control system worked flawlessly from the start. The first combat mission, flown on June 5, 1944 against railroad shops at Bangkok, Thailand, saw B-29 seconds encounter Japanese fighters for the first time. 98 B-29 seconds participated. 5 were damaged by fighters. Not one was shot down by fighter attack. The Japanese pilots, accustomed to attacking B-24 Liberators with their limited defensive firepower, discovered the B-29 was a completely different opponent. Captain Yasuhiko Kuro, a veteran pilot with the Imperial Japanese Army Air Force's 64th Sentai, described his first attack on a B-29 formation in his combat diary dated June 15, 1944. "We approached from 8 o'clock high, the standard attack angle that worked well against B, 24 seconds. Before we reached firing range, the American dorsal turrets began tracking us with unnatural smoothness. Their fire was precise and coordinated. 2 of our aircraft were hit before we could complete our attack run. We broke off. This was not like fighting previous American bombers. The early combat reports from the 20th Bomber Command reached the Pentagon in July 1944, and the statistical analysts couldn't believe what they were reading. B-29 gunners were achieving hit rates, averaging between 8 and 12% against Japanese fighters. For context, B-17 gunners over Europe, using traditional manually aimed guns, were averaging hit rates of approximately 2% in early 1943, improving to perhaps 5% by late 1944, with better training and computing sites. The B-29 seconds, in their very first combat operations, were hitting enemy fighters at rates double or triple what experienced B-17 crews achieved after years of combat and training refinement. Colonel Curtis LeMay, who would later take command of all B-29 operations against Japan, studied the early fire control data with particular interest. In a letter to General Henry Arnold, dated August 3, 1944, LeMay wrote, "The Central Fire Control system represents the single most significant advance in bomber defensive armament in aviation history. We're seeing kill ratios that shouldn't be possible. Japanese pilots are learning to fear the B-29 inches ways they never feared the B-24. The statistics behind this transformation were rooted in pure physics and mathematics. When a Japanese fighter attacked a B-29 from a classic beam attack angle, say 3 o'clock level, the combined dynamics created a targeting problem of extraordinary complexity. The Ki-61 Tony, one of Japan's premier interceptors, cruised at approximately 360 miles per hour. In an attack run, it might be traveling 400 miles per hour. The B-29, at combat weight, cruised at approximately 220 miles per hour at 25,000 feet. The closing rate during a beam attack approached 450 miles per hour, or 660 feet per second. A .50 caliber bullet left the muzzle of a Browning M2 at approximately 2,800 feet per second at sea level, but at 25,000 feet, where air density was only 1/3 of sea level, velocity and trajectory changed dramatically. At a typical engagement range of 400 yards, 1,200 feet, the bullet needed approximately 0.43 seconds to reach the target's position. During those 0.43 seconds, the attacking fighter moved 284 feet forward. The B-29 itself moved 95 feet forward. Both aircraft were also subject to vertical motion from turbulence, evasive maneuvering, and the natural porpoising that occurred in formation flying. For a human gunner trying to solve this equation manually, the cognitive load was overwhelming. He had to estimate range, judge target speed, calculate angular velocity, compensate for his own aircraft's motion, factor in altitude effects on bullet trajectory, adjust for parallax between his eye and the gun's bore axis, and somehow coordinate all these variables into a single precise aiming solution, all while wearing oxygen masks, fighting temperatures that could drop to -40 degrees Fahrenheit, and knowing that the attacking fighter's cannon shells would reach him long before his bullets reached the fighter. The B-29's General Electric Central Fire Control System solved this equation mechanically, continuously, and instantly. The Sperry computing site used a mechanical analog computer incorporating 27 gears, 14 cams, and 6 differential assemblies. When the gunner tracked a target and input wingspan, the computer measured angular rate of change, calculated range based on the wingspan input, factored in bomber airspeed from the aircraft's pitot static system, incorporated altitude from the aircraft altimeter, and computed the precise deflection angle required for bullet and target to arrive at the same point in space simultaneously. This computation happened continuously, updating 20 times per second, adjusting for every change in target position, bomber attitude, and flight dynamics. When the gunner squeezed his trigger, the guns didn't fire where the gunner was looking. They fired where the computer calculated the target would be when the bullets arrived. Technical Sergeant Howard Barnett, a Wright gunner with the 58th Bomb Wing, described the experience in a letter home dated September 19, 1944. "It's the strangest thing, shooting at absolutely nothing. You track the Japanese fighter in your sight, you see him at 2 o'clock, but your guns are pointing at 3 o'clock, aimed at empty sky. You pull the trigger, the red lights show your guns are firing somewhere in the airplane, and then you watch the Jap fly right into your bullets. It's like magic, except it's math." The Japanese response to this new defensive capability evolved rapidly through late 1944. Initial tactics that worked well against B-24 seconds proved suicidal against B-29 seconds. Beam attacks, the preferred approach for experienced Japanese pilots, exposed the attacker to the B-29's most effective defensive arc, where both dorsal and both ventral turrets could engage simultaneously under centralized control. Major Teruhiko Kobayashi, who flew 73 interception missions against B-29 seconds with the Imperial Japanese Army Air Force's 53rd Sentai, survived the war and later wrote extensively about his experiences. In a 1953 interview, he explained the tactical evolution. "At first, we attacked American B-29 seconds using the same methods we used against B-24 seconds. We lost pilots immediately. The B-29's defensive fire was too accurate, too coordinated. We learned to attack from 12 o'clock high, straight ahead and above, or from 6 o'clock low, directly behind and below. These angles gave the Americans fewer turrets that could engage us, but even then, their fire was deadly accurate. The American gunners weren't just good, their machines made them superhuman." The 12 o'clock high attack that Kobayashi described became the preferred tactic for Japanese interceptors by November 1944. Attacking from directly ahead minimized exposure time and limited the number of B-29 turrets that could effectively engage. But even this approach carried enormous risk. The B-29's forward dorsal turret, controlled by either the bombardier or the flight engineer depending on sector assignment, could engage targets from a nearly forward position. More critically, the computing site calculated deflection for head-on attacks with the same precision it calculated beam attacks. Staff Sergeant Vincent Carusi, a flight engineer gunner with the 73rd Bomb Wing, engaged his first head-on attack during a mission to Nagoya on January 3, 1945. His after-action report, preserved in the National Archives, describes the engagement with remarkable technical detail. Key 61, attacked from 12 o'clock high at approximately 1,000 yards range, diving at about 30-degree angle. I tracked him in the sight, set wingspan at 40 feet per intelligence identification, and waited for him to close. At approximately 400 yards, I squeezed the trigger. The forward dorsal turret engaged. I observed strikes on the fighter's wing root and engine cowling. The aircraft rolled left and went down trailing smoke. Time from initial sighting to enemy aircraft leaving formation was approximately 8 seconds. 8 seconds. That was the revolution. Traditional gunnery required sustained tracking, careful aim adjustment, and often multiple long bursts to achieve hits. The central fire control system reduced engagement time to single-digit seconds, while dramatically increasing hit probability. The Japanese recognized they were facing a technological leap they couldn't match. Japanese aircraft manufacturing, already struggling with resource shortages and strategic bombing, couldn't develop and field comparable systems. American engineers had spent 3 years and millions of dollars perfecting central fire control. Japan, fighting a defensive war with collapsing industrial capacity, had no equivalent development time or resources. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The November 1944 establishment of B-29 bases in the Mariana Islands, specifically Saipan, Tinian, and Guam, marked the beginning of sustained strategic bombing of the Japanese home islands. The missions from the Marianas were longer, the opposition more intense, and the stakes incomparably higher than earlier operations from China and India. The fire control system proved itself mission after mission. On January 27, 1945, 76 B-29 seconds attacked aircraft factories at Tokyo. Japanese fighters made aggressive interception attempts throughout the mission. The B-29 seconds claimed 47 enemy fighters destroyed with another 33 listed as probables or damaged. 8 B-29 seconds were lost to all causes, including flak. Only 2 losses were directly attributed to fighter attack. The exchange ratio was staggering. In European theatre operations, B-17 seconds and B-24 seconds typically suffered loss rates of 5 to 8% per mission during periods of heavy fighter opposition. The B-29 seconds, facing equally determined opposition from Japanese pilots, were losing less than 3% per mission, with fighter losses representing under 1%. The human dimension of this technological revolution deserves particular attention. The B-29 gunners weren't superhuman marksmen. They were ordinary young Americans, most barely 20 years old, plucked from farms, factories, and cities, given a few months of training, and sent to wage war at 30,000 feet over Japan. What made them extraordinarily effective wasn't their personal skill. It was their willingness to trust a system that violated every human instinct about combat. Master Sergeant Donald Cooper, a left gunner with the 314th Bomb Wing, flew 35 missions over Japan between February and August 1945. In a 1992 oral history interview, he reflected on the psychological aspects of the fire control system. You're sitting in this little compartment, can't see much except through your sighting station. Japanese fighters are attacking from every direction. Your hands are on controls that connect to guns you've never seen, guns that are mounted 30 feet away in turrets you can't even look at. You're aiming at empty sky, watching tracers go out toward absolutely nothing, and you have to believe, really, truly believe, that when that Japanese fighter reaches that empty sky, your bullets will be waiting for him. It went against everything that felt natural. But we learned to trust the system, because the alternative was death. The trust Cooper described wasn't blind faith. It was earned through demonstrated performance. Every mission provided tangible proof that the system worked. Gunners watched Japanese fighters fly into their fire patterns and explode. They saw damaged enemy aircraft trailing smoke, breaking off attacks, going down. The feedback loop was immediate and undeniable. The system saved lives, and the crews knew it. The statistical evidence compiled by the 20th Air Force Operations Research Section tells the story in stark numerical terms. During the period from November 1944 through March 1945, B-29 seconds flew 4,622 combat sorties against Japanese home island targets. Japanese fighters made an estimated 32,000 individual attack passes on these bombers. B-29 gunners claimed 943 enemy fighters destroyed, with another 611 listed as probables or damaged. Post-war analysis of Japanese records suggests the actual number of fighters destroyed or damaged by B-29 defensive fire during this period was approximately 650 aircraft, even using the more conservative post-war figures that represented a kill rate of approximately 2% per Japanese attack pass. For comparison, B-17 gunners over Germany achieved kill rates of approximately 0.5% per German attack pass during comparable periods in 1943 and early 1944. The B-29 gunners, using central fire control, were destroying enemy fighters at 4 times the rate achieved by manually aimed bomber defensive guns. The Japanese pilot experience provides equally compelling testimony. Captain Kaneyoshi Muto, who survived 47 interception missions against B-29 seconds flying with the 56th Sentai, was captured in August 1945 after being forced to bail out over Nagoya following combat damage. In interrogation reports, he described the psychological impact of facing B-29 defensive fire. Attacking American heavy bombers became a death sentence. not might be dangerous, not could result in losses, was a death sentence. In my squadron, we lost 62 pilots in 4 months of operations against B-29 seconds. That's nearly 3 complete squadron rosters. The American defensive fire wasn't just accurate, it was instant and coordinated. You began your attack run, and immediately multiple turrets swung to track you with mechanical precision. There was no hesitation, no hunting for position. The turrets simply pointed at you and fired. If you survived the first pass, you were lucky. If you tried a second pass, you were almost certainly dead. The technological superiority of the central fire control system created a psychological burden for American crews as well, though of a different nature. The system's effectiveness meant that B-29 gunners saw combat death up close and repeatedly. Technical Sergeant James Pritchard, a right gunner with the 505th Bomb Group, described an engagement over Osaka on March 13, 1945. Key 61 came in from 4 o'clock high. I tracked him, set my wingspan, waited for the range to close. At about 500 yards, I triggered the aft turret, watched my tracers walk right into his engine. The entire cowling exploded. Pieces of metal, probably cooling fins and engine parts, flew back past my sighting station. The fighter just disintegrated. Then I saw the pilot. He was on fire, falling past our formation, tumbling over and over. He couldn't get out. I watched him fall for at least 10 seconds before he dropped out of sight. That image stayed with me for 50 years. The March 9th through 10th, 1945 firebombing of Tokyo marked a tactical shift in B-29 operations. General Curtis LeMay, now commanding 21st Bomber Command, ordered B-29 seconds to attack at night from low altitude, 5,000 to 8,000 feet, carrying incendiary bombs instead of high explosives. The central fire control system, designed for high-altitude daylight defense, proved equally effective in low-altitude night operations. The psychological pressure on Japanese interceptor pilots intensified. Night interception required getting close enough to visually identify targets in darkness. Japanese fighters typically needed to close within 300 yards to be certain they were attacking B-29 seconds rather than friendly aircraft. At 300 yards, the B-29's central fire control made survival unlikely. The engagement window was simply too small. Japanese pilots reported that the moment they achieved visual identification, B-29 turrets were already tracking them, the computing sites having detected their approach through the optical sighting system's low-light capability. Lieutenant Fumihiko Tashiro, who flew night interceptions with the 53rd Sentai, described the experience. You search the darkness for the American bombers. You hear their engines, 4 massive radials per aircraft creating a sound like continuous thunder. You see their exhaust flames. You close to identify. Suddenly, tracers reach out from multiple positions simultaneously. You break away or you die. There is no middle option. The fire control system's effectiveness created an unexpected strategic problem. Japanese Fighter Command, recognizing the futility of conventional interception tactics, began pulling veteran pilots back from home island defense, preserving them for the anticipated invasion of Japan itself. Interception missions fell increasingly to less experienced pilots, often with under 100 hours total flying time, who were simply overwhelmed by the B-29's defensive capabilities. Master Sergeant Paul Henderson, a tail gunner with the 444th Bomb Group, noted this shift in Japanese pilot quality in his mission diary. Early missions, February and March, we faced aggressive, skilled pilots who used coordinated attacks and clever tactics. By May and June, we were seeing pilots who made basic mistakes, flew predictable patterns, didn't coordinate with other fighters. The fire control system was effective against good pilots. Against inexperienced pilots, it was absolutely devastating. We'd watch them set up attacks we could predict 5 seconds before they executed. The turrets were tracking them before they even started their final run. The numbers tell the grim story. In March 1945, Japanese interceptor forces lost an estimated 180 fighters to B-29 defensive fire. In April, 197. In May, 214. These losses, combined with pilot casualties from American carrier aircraft and P-51 Mustangs now operating from Iwo Jima, created an attrition rate Japanese training programs couldn't replace. The June 19, 1945 mission to the Ube coal liquefaction plant illustrated the complete dominance B-29 seconds had achieved. 474 superfortresses attacked in broad daylight. Japanese interceptors made fewer than 50 attack passes during the entire mission. Not a single B-29 was lost to fighter action. The Japanese had effectively conceded air superiority over their own home islands. The technological lessons learned from B-29 Central Fire Control extended far beyond World War II, influencing military weapons development for decades. The principle of remote weapons control, centralized computing, and coordinated fire became fundamental to modern combat systems. The B-52 Stratofortress, which entered service in 1952, incorporated an advanced version of centralized fire control for its tail position, controlled from the main crew compartment. Modern armored vehicles use remotely operated weapon stations that trace their conceptual lineage directly to B-29 turrets, the Phalanx close-in weapon system, defending U.S. Navy vessels today, employs radar-directed, centralized fire control to engage incoming missiles, the same basic principle as B-29 gunners engaging incoming fighters. The system tracks threats, calculates intercept solutions, and fires guns remotely, all without direct human aim. Modern fighter aircraft, like the F-35, use sensor fusion, combining data from multiple sources to create targeting solutions, a direct evolution of the integrated fire control concept pioneered on the B-29. The revolution in aerial gunnery, represented by central fire control, marked a fundamental shift in how humans interfaced with weapons systems. For thousands of years, from the first archer drawing a bow to the B-17 gunners over Germany, marksmanship had been about the individual warrior's skill, judgment, and direct control of his weapon. The B-29 system fractured this ancient relationship. The gunner became an operator, feeding data to a computer that made the actual aiming decisions. The guns became remote executors of mathematical calculations. The act of killing became mediated through electronics, hydraulics, and analog computation. Dr. Thomas Hughes, a historian of technology at the University of Pennsylvania, analyzed this transformation in his 1987 book, American Genesis. He wrote, "The B-29 Central Fire Control System represented the first widespread military application of what we now call human-machine interface. The gunners weren't fighting enemy aircraft. They were managing a complex technological system that fought enemy aircraft. This distinction might seem subtle, but it fundamentally changed the nature of aerial combat and foreshadowed the computer-mediated warfare that would dominate the late 20th and early 21st centuries. The human cost of this technological revolution, both American and Japanese, shouldn't be abstracted into statistics. Every percentage point of improved hit rate, every Japanese fighter destroyed, every bomber that made it home safely, represented individual human lives saved or lost." Staff Sergeant Robert Kennedy, a left gunner with the 31st Bomb Group, survived his combat tour and returned home to Pennsylvania in October 1945. In a 1998 interview, he reflected on what the fire control system meant to him personally. "I don't think about the mathematics or the technology. I think about the men in my crew who came home because that system worked. Our pilot, Lieutenant Morrison, got married 2 months after we got back. He has 4 grandchildren now. Our bombardier, Captain Pierce, became a high school principal. Our radar operator, Sergeant Chen, opened a restaurant in San Francisco. The fire control system didn't just improve our hit rates by some statistical percentage. It gave 34 men in our squadron the chance to live their lives. That's what technology means to me. Not the gears and hydraulics, but the lives it saved." The B-29 gunners themselves, those young men who learned to trust machines over instinct, returned home to an America that had fundamentally changed during their absence. Many struggled to articulate what they'd experienced. How do you explain to someone who hasn't been there what it feels like to shoot at empty sky while death approaches at 400 miles per hour? How do you describe trusting a computer you don't understand to save your life? Master Sergeant Arthur Klein, who flew 42 missions as a right gunner, later wrote in his unpublished memoir about the disconnection he felt. We came home to parades and celebrations, and people would ask what it was like. I'd try to explain the fire control system, how we aimed at nothing and hit everything, and they'd look at me like I was making it up or maybe crazy. It sounded like science fiction. But it was real. It was the most real thing I've ever experienced. We lived because we learned to trust machines more than ourselves. That's a hard thing to explain to someone who's never had to make that choice. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.